When dealing with an 800 amp service, several options exist for setting up the service disconnect. Let's explore these different approaches. One option is to use an 800 amp service entrance rated switchboard. This consists of a single enclosure that houses either a fused or unfused main breaker rated for 800 amps. The advantages of using a switchboard include its compact design and ease of maintenance. However, switchboards can be expensive and may not be easily scalable if future requirements increase. Another approach involves using 400 amp service entrance rated panel boards parallel to the current transformer, or CT. In this setup, you would use two 400 amp service entrance rated panelboards, each equipped with main breakers rated for 200 amps. The current transformer inputs are then parallel to the meter. One of the benefits of this approach is that it can be less expensive than a single 800 amp switchboard. Keep in mind that this method takes up more space and might necessitate a separate enclosure for the current transformers. A third option involves using 400 amp service entrance rated panel boards with main lug mains. This entails using two 400 amp service entrance rated panel boards with main lug terminals. A single 800 amp main breaker is then installed in an external enclosure, such as a meter base. This option provides flexibility for future expansion, as you can add more panels if needed. However, it does require an external main breaker and may not be as compact as other solutions. Now, let's discuss the choice between using a fused or unfused disconnect. The decision of whether to use a fused or unfused service disconnect often hinges on local code requirements and the specific requirements of the utility company. Many utility companies mandate the use of fuses for services exceeding a certain amperage. Fused disconnects offer a recurrent protection, whereas unfused disconnects rely on the main breakers within the panel boards for protection. Considering remote panels, the two 150 amp remote panels can be connected to the main service disconnect using conduits and appropriately sized feeder cables. Similarly, the two 200 amp outside panels can be treated as sub-panels and connected to the main service disconnect in the same manner, again ensuring proper conduit and feeder cable sizing. Additional considerations are crucial for a successful installation. Firstly, consult with the local authority having jurisdiction, or OJ, to ensure compliance with specific requirements and regulations. Secondly, meticulous planning is essential for proper wire sizing, conduit selection, and grounding techniques. Thirdly, confirm that the service equipment is adequately rated for the anticipated load requirements of the installation. Finally, secure all necessary permits and undergo the required inspections from the authority having jurisdiction to ensure the installation is safe and compliant. In summary, the choice of service disconnect configuration depends on factors such as cost, space constraints, future scalability needs, and local code requirements. Consulting with a qualified electrician and the local authority having jurisdiction is highly recommended to ensure a safe and compliant installation. The proper sizing of conductors for an 800 amp service is crucial for safety and compliance with the National Electrical Code, or NEC. The NEC provides specific guidelines and tables for determining the appropriate conductor size based on the ampacity, insulation type, and installation conditions. For an 800 amp service, you will typically use multiple conductors in parallel to achieve the required ampacity. The NEC addresses this in section 310.10, which covers conductors in parallel. When conductors are installed in parallel, they must meet certain requirements to ensure that the current is evenly distributed and that the conductors operate safely. These requirements include being the same length conductor material, circular mill area, insulation type, and being terminated in the same manner. To determine the conductor size, you need to consider the ampacity of the conductors and any applicable dilating factors. The NEC provides ampacity tables for different conductor types and insulation ratings in Article 310. For example, Table 310.16 lists the allowable ampacities for insulated conductors rated up to 600 volts, based on the conductor temperature rating and the ambient temperature. Let's assume you are using copper conductors with a temperature rating of 75 degrees Celsius. According to Table 310.16, a 500 kc mil copper conductor has an ampacity of 380 amps. Since you need to carry 800 amps, you would need to use at least 3 500 kc mil conductors in parallel per phase. To verify this, multiply the ampacity of a single conductor by the number of conductors in parallel. 380 amps times 3 conductors equals 1140 amps, which exceeds the required 800 amps. The NEC also requires that the overcurrent protection device, such as the circuit breaker or fuses, be sized to protect the conductors. The overcurrent protection device should not exceed the ampacity of the conductors it protects. In this case, the 800 amp service disconnect would provide the overcurrent protection for the service entrance conductors. It is important to consider any applicable derating factors that may reduce the ampacity of the conductors. Derating factors are applied when conductors are installed in certain conditions, such as in close proximity to other conductors or in high ambient temperatures. Table 310.15b3 in the NEC provides adjustment factors for the number of current-carrying conductors in a raceway or cable. If multiple conductors are installed in the same raceway, the ampacity of each conductor must be reduced according to the adjustment factors in the table. For example, if you have more than 3 current-carrying conductors in a raceway, the ampacity of each conductor must be derated. The amount of derating depends on the number of conductors and the specific conditions of the installation. In addition to derating for the number of conductors, you may also need to derate for high ambient temperatures. Table 310.15b2 in the NEC provides correction factors for ambient temperatures other than 30 degrees Celsius. If the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductors must be reduced according to the correction factors in the table. To ensure compliance with the NEC, it is important to consult the latest edition of the code and follow all applicable requirements. A qualified electrical engineer or electrician can assist with determining the appropriate conductor size and ensuring that the installation meets all safety and code requirements. Grounding is another critical aspect of an 800 amp service installation, and it must be done correctly to ensure the safety of the electrical system and prevent electrical shock hazards. The NEC provides specific requirements for grounding in Article 250, which covers the grounding and bonding of electrical systems. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source, which allows the overcurrent protection device to quickly trip and energize the circuit in the event of a fault. This helps to prevent electrical shock hazards and reduce the risk of fire. The grounding system typically consists of a grounding electrode, a grounding electrode conductor, and a bonding system. The grounding electrode is a conductive object that is buried in the earth and provides a connection to ground. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The grounding electrode conductor connects the grounding electrode to the service equipment, such as the main service disconnect. The bonding system connects all non-current carrying metal parts of the electrical system together, such as metal conduits, enclosures, and equipment grounding conductors. This helps to create a low impedance path for fault current to flow back to the source. For an 800 amp service, the NEC requires the use of a grounding electrode system that consists of one or more of the following grounding electrodes: a metal underground water pipe in direct contact with the earth for at least 10 feet, a ground rod that is at least 8 feet long and 5/8 inch in diameter, or a ground plate that has a surface area of at least 2 square feet. The grounding electrode conductor must be sized according to Table 250.66 in the NEC. The size of the grounding electrode conductor depends on the size of the service entrance conductors. For an 800 amp service, the grounding electrode conductor must be at least 3/0 copper or 250 kc mil aluminum. In addition to the grounding electrode conductor, the NEC also requires the use of an equipment grounding conductor to connect the non-current carrying metal parts of the electrical system to the grounding system. The equipment grounding conductor must be sized according to Table 250.122 in the NEC. The size of the equipment grounding conductor depends on the size of the overcurrent protection device protecting the circuit. For an 800 amp service, the equipment grounding conductor must be at least 1/0 copper or 3/0 aluminum. Bonding is another important aspect of grounding. All non-current carrying metal parts of the electrical system must be bonded together to create a low impedance path for fault current to flow back to the source. Bonding is typically accomplished by using bonding jumpers to connect metal conduits, enclosures, and equipment grounding conductors together. The NEC also requires the use of a main bonding jumper to connect the grounded conductor to the equipment grounding conductor of the service equipment. The main bonding jumper must be sized according to table 250.28 in the NEC. For an 800 amp service, the main bonding jumper must be at least 1/0 copper or 3/0 aluminum. Proper grounding and bonding are essential for the safe and reliable operation of an electrical system. It is important to follow all applicable requirements in the NEC and consult with a qualified electrical engineer or electrician to ensure that the grounding system is properly designed and installed. When installing an 800 amp service, conduit selection is a critical consideration to ensure the safe and reliable routing of electrical conductors. The NEC provides guidelines for selecting appropriate conduit types and sizes based on factors such as the number and size of conductors, installation environment, and mechanical protection requirements. Conduit serves to protect conductors from physical damage, moisture, and other environmental factors, while also providing a raceway for pulling conductors through. The NEC specifies various types of conduit, each with its own characteristics and applications. Common types of conduit include rigid metal conduit, or RMC, intermediate metal conduit, or IMC, electrical metallic tubing, or IM, flexible metal conduit, or FMC, and rigid polyvinyl chloride conduit, or PVC. Rigid metal conduit is a heavy-duty conduit made of steel or aluminum, offering excellent mechanical protection and resistance to corrosion. It is suitable for both indoor and outdoor applications, including direct burial in concrete or underground. Intermediate metal conduit is similar to rigid metal conduit but is thinner and lighter, making it easier to work with. It provides good mechanical protection and is suitable for a wide range of applications. Electrical metallic tubing is a lightweight conduit made of steel or aluminum, commonly used for indoor applications in dry locations. It is easy to cut and bend, but it provides less mechanical protection than rigid metal conduit or intermediate metal conduit. Flexible metal conduit is a flexible conduit made of steel or aluminum, used for connecting equipment or for installations where flexibility is required. It provides limited mechanical protection and is not suitable for direct burial or wet locations. Rigid polyvinyl chloride conduit is a non-metallic conduit made of polyvinyl chloride, offering excellent resistance to corrosion and chemicals. It is suitable for underground or wet locations, but it is not as strong as metal conduit and may require additional support. When selecting conduit for an 800 amp service, you need to consider the number and size of conductors that will be installed in the conduit. The NEC provides tables that specify the maximum number of conductors allowed in different conduit sizes based on the conductor size, installation type, and conduit type. These tables can be found in Chapter 9 of the NEC. To determine the appropriate conduit size, you need to calculate the total cross-sectional area of all the conductors that will be installed in a conduit. Then, you can consult the NEC tables to find the conduit size that can accommodate the total cross-sectional area of the conductors. It is important to note that the NEC also limits the percentage of the conduit's cross-sectional area that can be occupied by conductors. This is to ensure that there is enough space for heat dissipation and to prevent damage to the conductors during installation. In addition to the number and size of conductors, you also need to consider the installation environment when selecting conduit. If the conduit will be exposed to corrosive environments such as saltwater or chemicals, you should use a conduit material that is resistant to corrosion, such as rigid polyvinyl chloride conduit or coated metal conduit. If the conduit will be installed in a location where it may be subject to physical damage, such as in a manufacturing plant or construction site, you should use a conduit material that provides adequate mechanical protection, such as rigid metal conduit or intermediate metal conduit. The NEC also provides requirements for supporting and securing conduit to prevent it from sagging or becoming damaged. Conduit must be supported at intervals specified in the NEC using appropriate straps, clamps, or hangers. The type of support used depends on the type of conduit and the installation environment. Proper conduit selection and installation are essential for the safe and reliable operation of an 800 amp service. It is important to follow all applicable requirements in the NEC and consult with a qualified electrical engineer or electrician to ensure that the conduit system is properly designed and installed. Overcurrent protection is a critical safety feature in an 800 amp service installation designed to protect electrical circuits and equipment from damage caused by excessive current flow. Overcurrent can result from various factors such as short circuits, overloads, or ground faults. The NEC provides specific requirements for overcurrent protection in Article 240, which covers the types of overcurrent protection devices, their ratings, and installation requirements. The primary function of overcurrent protection is to interrupt the flow of current in a circuit when it exceeds the safe operating limits. This is typically accomplished by using fuses or circuit breakers. Fuses are one-time use devices that contain a fusible link that melts and opens the circuit when the current exceeds the fuse's rating. Circuit breakers are reusable devices that trip and interrupt the circuit when the current exceeds the breaker's rating. Circuit breakers can be reset manually or automatically after the overcurrent condition has been corrected. For an 800 amp service, the NEC requires the use of overcurrent protection devices that are rated to interrupt the maximum available fault current at the service entrance. The available fault current is the amount of current that would flow in a circuit under fault conditions such as a short circuit. The available fault current can be calculated based on the utility company's supply voltage and impedance, as well as the impedance of the service entrance conductors and equipment. The overcurrent protection devices must have an interrupting rating that is equal to or greater than the calculated available fault current. The NEC also provides requirements for the location and accessibility of overcurrent protection devices. Overcurrent protection devices must be readily accessible and located in a safe place where they can be easily inspected and maintained. They should not be located in areas where they could be exposed to moisture, corrosive fumes, or physical damage. The size and type of overcurrent protection devices used in an 800 amp service depend on the specific characteristics of the electrical system and the loads being served. The NEC provides tables and guidelines for selecting the appropriate overcurrent protection devices based on the conductor size, installation type, and the type of load being served. For example, the NEC requires the use of inverse time circuit breakers for most general purpose circuits. Inverse time circuit breakers trip faster as the overcurrent increases, providing better protection against overloads and short circuits. In addition to the main overcurrent protection devices at the service entrance, the NEC also requires the use of overcurrent protection devices for branch circuits and feeders that are connected to the service. Branch circuits are the circuits that supply power to individual loads such as lighting fixtures, receptacles, and appliances. Feeders are the circuits that supply power to branch circuit panels or other sub-distribution equipment. The overcurrent protection devices for branch circuits and feeders must be sized to protect the conductors and equipment they serve. Proper overcurrent protection is essential for the safe and reliable operation of an electrical system. It is important to follow all applicable requirements in the NEC and consult with a qualified electrical engineer or electrician to ensure that the overcurrent protection system is properly designed and installed. The authority having jurisdiction, or UJ, plays a crucial role in the installation of an 800 amp service. The authority having jurisdiction is the governmental agency or organization responsible for enforcing electrical codes and regulations in a specific area. The AHJ may be a local building department, a state electrical board, or another regulatory agency. The primary responsibility of the authority having jurisdiction is to ensure that electrical installations are safe and comply with all applicable codes and regulations. This is typically accomplished through a process of permitting, inspections, and enforcement. Before beginning any electrical work, including the installation of an 800 amp service, it is important to obtain the necessary permits from the authority having jurisdiction. The permit application typically requires detailed information about the proposed electrical work, including drawings, specifications, and calculations. The AHA reviews the permit application to ensure that the proposed work complies with the electrical code and other applicable regulations. Once the permit is approved, the electrical work can begin. However, the AHA typically requires inspections at various stages of the installation to ensure that the work is being performed in accordance with the approved plans and specifications. The inspections may include a rough-in inspection, which is performed before the electrical work is covered up, and a final inspection, which is performed after the electrical work is complete. During the inspections, the AHA inspector examines the electrical work to ensure that it meets all applicable code requirements. This may include checking the size and type of conductors, the installation of overcurrent protection devices, the grounding and bonding system, and other aspects of the electrical installation. If the inspector finds any violations of the electrical code, they may issue a notice of violation, which requires the contractor to correct the deficiencies. The electrical work cannot be approved until all violations have been corrected and the installation complies with the code. In addition to permitting and inspections, the authority having jurisdiction also has the authority to enforce the electrical code. This may include issuing fines, suspending or revoking licenses, or taking other legal action against contractors who violate the code. The specific requirements and procedures of the authority having jurisdiction may vary depending on the location. It is important to contact the local AHA to determine the specific requirements for electrical installations in your area. Consulting with the authority having jurisdiction early in the planning process can help to avoid costly delays and ensure that the electrical installation is safe and compliant. It is also important to maintain good communication with the AHA throughout the installation process to address any questions or concerns that may arise. Working closely with the authority having jurisdiction is essential for ensuring that the installation of an 800 amp service is performed safely and in accordance with all applicable codes and regulations. In summary, the installation of an 800 amp service is a complex and critical undertaking that demands meticulous attention to detail and adherence to the NEC and local regulations. Throughout the process, from initial planning and design to final inspection and approval, several key aspects must be carefully considered. Firstly, the selection of service disconnect options should align with factors such as cost, space constraints, future scalability needs, and local code requirements, often necessitating consultation with qualified professionals and the AHA. Secondly, conductor sizing must comply with NEC guidelines, taking into account ampacity, dirting factors, and installation conditions to ensure safe and efficient current carrying capacity. Thirdly, proper grounding and bonding are essential for preventing electrical shock hazards and ensuring the safe operation of the electrical system, requiring adherence to NEC Article 250 and the use of appropriate grounding electrodes, conductors, and bonding jumpers. Fourthly, conduit selection must consider the number and size of conductors, installation environment, and mechanical protection requirements, with careful attention to NEC guidelines for conduit fill and support. Fifthly, overcurrent protection devices, such as fuses and circuit breakers, must be appropriately sized and rated to protect electrical circuits and equipment from damage caused by excessive current flow, in accordance with NEC Article 240. Finally, collaboration with the authority having jurisdiction is crucial for obtaining necessary permits, undergoing inspections, and ensuring compliance with all applicable codes and regulations, facilitating a safe and code-compliant installation. By diligently addressing these key aspects and working closely with qualified professionals and the authority having jurisdiction, the installation of an 800 amp service can be successfully executed, providing a reliable and safe electrical supply for the intended application.